Okay, this tutorial is about terminal velocity. It's all about Newton's laws and making connections. So we're going to talk about Newton's second law, Newton's first law, and most importantly, Newton's third law, which plays a big role in terminal velocity. Okay, so what is terminal velocity? Well, and this is something you're definitely going to want to write down on a piece of paper and highlight it. Terminal velocity is the maximum velocity at which an object will fall through a liquid or gas. So when objects fall through, whether it's through the air, through water, through oil, whatever the case may be, the object will accelerate for some short period of time, but will soon reach a speed. So it'll accelerate and then reach a speed where it just falls at a nice constant speed. That happens when the upward resistive force balances the force of gravity acting on the object. At that point, the object will stop accelerating. And if the forces are balanced, Newton's second law says that if the forces are balanced, it will fall at a constant terminal speed. Okay. Now, there's a lot of factors that play a role in what that maximum terminal velocity will be for an object. It has to do with the shape of the object, the mass of the object, what the object's falling through, and some other factors as well, so surface area and things like that. So it's really important, and it's Newton's third law, and we're going to see how that plays a role in just a few minutes. Okay, terminal velocity. So on the download that you got, it has a sheet. And so you're just going to look at the sheet and highlight any key points. So it says here what terminal velocity is. Terminal velocity is reached once the force of gravity is balanced with the upward reaction force of the air. So as you're falling through the air or through the fluid, whatever the case may be, you are, or the object is pushing against that fluid and that, or that gas. And if it pushes against it, there's an upward force of that object or of that gas or that fluid on the object. Newton's third law: the forces are equal and opposite, but in the opposite direction. So when terminal velocity is reached, the acceleration is zero. So when terminal velocity is reached, the acceleration is zero, which implies that the net force acting on the object is zero. And therefore, since it was already moving, it had accelerated to some position or some speed, it will maintain that exact speed. So if we consider a skydiver like here, the instant you jump out of a plane, or jump out of, in this case, a plane or off a cliff, the instant you do that, you will accelerate at 9.8 meters per second initially. Now, as soon as you start picking up some speed, you're pushing against the air. Well, the air starts to push against you. And you can see here that the air resistive force is increasing. Now, since the force of gravity, the pull of Earth on your body, is bigger than the force of the air, you continue to accelerate. And so you pick up speed continually because the force of gravity is still bigger than the air resistive force. So you'll continue to accelerate. However, the acceleration is reducing as time goes on. The faster you go, this air force, this force of the air gets bigger and bigger, means that you're slowly decelerating. You're not going as fast as you were before. So you're not accelerating at the same rate as 9.8. You might drop to 7, 6, 5, 4, 3, 2, 1, and eventually you'll reach a specific speed called the terminal velocity, where the gravitational force pulling down is matched by the upward resistive force due to that speed, or the force you're applying to the fluid or the liquid, or the gas, and they'll be balanced. The forces will be equal, and you will move at that constant speed. Okay. Here's an example. Your guy jumps out of a helicopter, and you can see that the air resistive force keeps increasing. And there you go. So now it's kind of hard to watch, but you'll see that it's balanced at 1,000, so there's no acceleration. He moves at a constant speed. When he first jumps out, he's accelerating at 10 meters per second. Starts to slow down. The acceleration is reducing. Finally reaches zero. Pulls the chute. Force goes up, and then he eventually reaches his terminal speed. Now, what's important here is that during this fall, the initial bit, you can see the air force gets bigger and bigger until it's balanced. Now, when you first pull this chute, a lot of people mistakenly think that you move upwards. You don't. You just slow down. So you're still moving downward, but you're slowing down. That jerk that you feel, or that you think that you see in movies, when someone pulls a chute, you see them go up. The reason you're seeing them go up is because the person videotaping them is still falling. And so relative to the person who's falling, it looks like the person's going up, but all they did was slow down. So you really need to be careful and really think about what's happening, when you see these questions. There's so many things that are out there that fool you into thinking the wrong things. And that is an example of that. Okay, so hopefully you've watched this a little bit and kind of get the idea of what's happening. Base jumping is pretty wild. People jump out in these squirrel suits, these wing suits, and what they're able to do is with those wing suits, they can increase their surface area. And by increasing their surface area, they're able to not fly because you can't get lift. But what they can do is reach a terminal speed that is quite fast, still very, very quick. But the wingsuits allow them to maneuver until they reach a height at which it's safe and away from the rocks where they can pull their ripcord and pull out a chute. So let's take a watch. It's just awesome stuff. So they're always moving down, right? They can't go up. They're always moving down just at a terminal speed. And these cliffs are big enough and high enough that they're able to reach that terminal velocity really quickly. Without the wingsuits, you wouldn't reach terminal velocity fast enough, and you wouldn't be able to have any control. That guy's just doing a regular jump, and he's going to pull his chute. There are so many videos online for this, so when you're done watching this video, I would suggest you go and search some up. It's very dangerous. Now these kind of cliffs that they're jumping off are called terminal cliffs. And they're called terminal cliffs because they allow you to reach terminal velocity, which is important. Then you can do all kinds of fun tricks. Notice when he tucks in, he starts to accelerate again because he's got to reach his new terminal velocity. This is a lower terminal velocity than when in your dive position. And you can see him stealing away. Oh man, people have way. Oh my goodness. That guy doesn't even have a wingsuit on. I didn't realize people did this without wingsuits too. You have a little less control, I think, and your terminal velocity will be a little bit faster, a little bit higher, and it'll take you longer to reach that terminal velocity, but apparently you can still do it. Alright, so with that being said, I would say watch those videos. Alright, something here that's neat, and if you download the video, you can actually go to an online calculator that I've had some students make that help you calculate what your terminal velocity will be. And you don't need to know this equation, but some of you might find this pretty interesting. So this is for any object falling through a fluid or a gas. If you take 2 times the mass, so if you know the mass of the object, let's say a person, multiplied by the gravity, so 9.8 meters per second, you can do this on different planets too. If you know the density of the fluid that you're falling through, so that you can just look that up, you can literally search up density of fluids. If you know the surface area of the object, so whether you're flattened out or whether you go into a dive. If you go into a dive, the area becomes smaller. If you're flatten your body out, the area becomes bigger. And the last one is called the drag coefficient. And again, that is dependent on the shape of the object, whether it's a circle, a triangle, a flat surface, a box, a teardrop, a raindrop, any kind of shape. These are just numbers. You plug them in and it tells you what your terminal velocity will be for that object. So you can see what effect density, area, and drag coefficient have. If there's a very low drag coefficient, like a cylinder or bullet shape object, or a person that's in a dive, that means you have a low surface area, you have a low drag coefficient, and if you're in a very low density gas, the whole entire denominator is really small. Well, if the denominator is small and the top is constant, ignoring, you don't even need to worry about the square root. If the bottom number is small, your terminal velocity is big. If you have a big density like water and a flat surface like a big flat rock and a big drag coefficient because it's a flat object, these numbers are big. And if the number is big on the bottom, you get a small terminal velocity. And that's why when you drop a rock in water or you jump into water, you reach terminal velocity almost instantly. Whereas if you take a rock that's massive and you have a small area of it and it's got a lot of mass and a gas with a certain shape, like a round shape to it, it will fall through the air really, really quick and reach, hundreds of kilometers an hour in terminal velocity. On planets where gravity is less, the terminal velocity is smaller as well. So even though we're not going to use this equation, you can quickly see what effects what effects these variables have on the equation. And if you download this thing, you can actually view the online calculator. In fact, maybe I'll pull it down and show it to you in a minute. Okay, now for your notes. On that sheet, where it had the thing about terminal velocity, you can write in the back the law of falling bodies. Pause this and write it down. The law of falling bodies is if there's no air resistance, all objects, regardless of their mass, fall with the same acceleration, and there is no terminal velocity. Right? If there's no air resistance, there's no terminal velocity. The thing will just accelerate and accelerate and accelerate until it hits the ground. Like things on the moon, they don't reach terminal velocity because there's no air resistance. Okay, and Newton's, the Galileo talked about this, how, we learned about inertia and that, just because the force of gravity on objects might be bigger, they have more mass, more inertia, and therefore they still accelerate at the same rate regardless of the mass of the object. Now, if there is air resistance, if you increase the air resistance, this causes the objects to reach terminal velocity more quickly and results in a lower terminal velocity. So if you increase resistance, air resistance, you reach terminal velocity fast and the terminal velocity is small. If you increase the surface area, so flatten an object out, it will reach terminal velocity more quickly and it will result in a lower terminal velocity. If you increase the object's density, meaning put a lot of mass in a small volume, it will reach terminal velocity more slowly and reach a high terminal velocity. Pause this, write this stuff down. And if you wanted to as well, you could write down that equation that we talked about before. Here's a whirligig activity that I love to do. And you can build this on your own. The directions are on the next page. And you can see how you can drop them and check out how slow they move. It's sort of like a helicopter seed from a tree. And I'll go back. Here's what it looks like. You just cut a piece of paper, cut down the middle, fold it out, put some weights on it, and you can make it as big or as small as you want. Draw on it, color it, and here are the results. And you'll see the drop. And you see there, some of those really, really slowly. I think it's this one here, maybe. Watch how slow it goes. It reaches terminal velocity really, really fast, and the spinning of it using Newton's third law says as it's pushing down in the air is pushing up on it, and those things reach terminal velocity very fast. If you want to build one, it is, and we're going to do it in class, and we will have a challenge as well and see will reach terminal velocity the fastest, and therefore have the slowest terminal velocity and reach the ground in the longest amount of time.